So welcome to proving something isn't differentiable at a point. So your first thought may be, WTF? Wow, that's fantastic, because it is. So let's get started. So for something to be differentiable, two things have to be happening. Number one, it has to be continuous, and number two, the limit of the derivative has to exist. So what does it mean for it to be continuous? Well, it just means that f of c has to equal the limit of f of x on both sides of c. And then for the derivative to exist, it just means that the limit of f prime of x has to equal the limit of f prime of x on both sides, which basically means the slopes are equal on both sides. So there's four main cases when something isn't differentiable. So let's take a look at those graphs. The first one is usually with an absolute value graph, but it's a sharp corner. The second one is a discontinuity like a hole. The third one is a discontinuity like asymptotes. And the fourth one is when there's a vertical tangent line. So it's easy to see why it's not differentiable at those two, because it's not continuous. But this one is trickier. When there's a vertical tangent line, that means that the slope of the tangent line is infinity, and we can't really do anything with that. So we say that it's not differentiable. And then when there's a corner, the slopes on both sides switch instantly at that point. So it's not like a parabola where it's a slow transition. The slope is just different on both sides, so they're not equal to each other, so it's not differentiable. So when trying to figure out if something's differentiable at a point, first check if it's continuous. If not, it's not differentiable. And if it is, make sure the derivatives on both sides of the point are equal. And if so, then it's differentiable. So how do you actually write out and prove that something's not differentiable? Well, let's start with the simple graph. Here we have a parabola with a point of discontinuity at 3. So we can immediately tell that it's not continuous, so it's not differentiable. But how do we write that out? Well, you use the limit notation. So we see that f of 3 doesn't equal the limit as x approaches 3 of f of x, which implies that it's discontinuous. Therefore, f of x isn't differentiable at x equals 3. Now, when we have to prove that something isn't differentiable when it's continuous, it's a little trickier. So let's look at this absolute value and figure out if f of x is differentiable at x equals 3. Well, we could start by graphing it, and from there we would see that it is continuous. However, there's that corner, so we know that it's not differentiable. But to prove that, we can start by writing the piecewise of f of x. So we can split this into the two separate lines and write the equations for both of those in the piecewise. So x minus 3 when x is greater than or equal to 3, and the negative version of that when x is less than 3. So now it'll really help to write the piecewise for f prime, and this is how we're going to prove it's not differentiable. So the derivative of x equals 1, the derivative of negative x equals negative 1. And if we wanted to graph this, we would see that at 3, the slopes are not equal to each other. Therefore, f of x isn't differentiable at x equals 3. And to write that out, we would write the limit as x approaches 3 from the left of f prime doesn't equal the limit as x approaches 3 from the right of f prime of x. Because even though this class has got me confused about most things, I'm still pretty sure that 1 doesn't equal negative 1. So for our last example on how to disprove differentiability, we're going to look at something a little more complicated, which is just a piecewise of a quadratic and a linear function. So if we wanted to graph this like we graphed the last one, it's really not going to be as helpful. All it's going to show is that it's continuous, but from the graph we can't figure anything out about the slopes. Now, if you wanted to determine if something's continuous without graphing it, you would just set both sides equal to each other and plug in the x value. So here we can see that 7 does equal 7, so it is continuous. And now we know that we have to be looking at the derivatives. So once again, we're going to write the piecewise for the derivatives. The derivative of 3x squared equals 6x. The derivative of 7x equals 7. And then we can plug in 1 on both of those, so find the limit of the derivative of 1 from the left and the right. And I meant to write g prime of x, but I wrote f prime of x. Sorry. But anyways, we can see that the limit from the left is 6 and from the right is 7, which once again do not equal each other, so it's not differentiable. And then to write this answer in the proper notation, you should include the limit of x as x approaches 1 from the left of g prime of x, but I forgot, so sorry. But anyways, it's not differentiable at x equals 1. And this notation is a son of a gun, so just be careful. So you might see problems that ask you to apply this knowledge of differentiability. So a common one will give you piecewise of something with variables, and you have to figure out what the variables are to make it differentiable. So we know that for something to be differentiable, it has to be continuous, and then the derivatives are going to have to be equal to each other. So in this case, it's at 2. And using that knowledge, you can write your two equations. So if it's continuous, then ax squared plus 10 is going to have to equal x squared minus 6s plus b when x equals 2. So you just plug 2 in for x, and then you'll get 4a plus 10 equals negative a plus b, so b equals 4a plus 18. And then with the differentiability aspect, with the derivatives, which is a tongue twister, anyways, you're going to have to make the derivatives equal to each other. So ax squared is going to be 2ax, and it's going to have to equal 2x minus 6, and then plug 2 in for 6, so we'll get 4a equals 4 minus 6, so 4a equals negative 2, so a equals negative 1/2, and then just plug that back into our other equation. And then b is going to equal 16, so just use the two aspects of differentiability, and then you can make your equations from that. But for the most part, when you're proving or disproving differentiability, just follow these steps. So first, determine if it's continuous. You can use a graph, you can plug in x. If it is, then write the f of x piecewise, then write the f prime of x piecewise. It's not pennywise from it, although this is my biggest fear, it's piecewise. Anyways, compare f prime on both sides, and hopefully they should be equal to each other if you're trying to prove it, and they shouldn't be equal if you're disproving differentiability, and then use that messy notation. Oh, and I forgot the most important step. When you see it, cry. Anyways, some common mistakes to look out for. The biggest one is thinking that continuity means it's differentiable. It does not guarantee differentiability. If something's not continuous, you know it's not differentiable, but if you know something's continuous, it doesn't have to be differentiable. That's why the absolute value graphs confuse so many people. The next one are with when the asymptote is going in the same direction. Sometimes people think that because the limit might technically be infinity or negative infinity, that it's differentiable, but it's not, because it's not continuous and the slopes aren't equal to each other. So just be careful for that, and then remember that vertical tangent lines mean that the tangent slope is going to be infinity and it's not differentiable there. So thank you for joining me as we discussed one of the most riveting concepts in science, mathematics, history, fashion, religion, and good luck on the test.